Format for this experience is we're going to have weekly lectures. In the lectures, we really don't have that much time, and so we can only really touch on the important stuff. Then there's a reader that we're putting together, and the reader has the sort of deep learning that you'll be doing. And so there's several selections that you'll need to work through, and then there's a collection of problems that go along with that. So your main task is to complete the problems. So if you feel like just seeing the lectures is enough, you can just jump into the problems. But there is some reading that I think you'll probably have to do just because we don't have too much time here, actually. All right. So we're going to start at something that everybody knows already, but we just kind of have to start somewhere, right? And we're going to start with the basic interest equation. So we have something called a nominal interest rate.
Unique super interest.
Yeah, exactly. So the nominal interest rate is surprisingly difficult to define. That's something that you know it when you see it, but the definition's a little bit cryptic. So if you were going to define it formally, you'd say an interest rate expressed relative to a given time frame that may or may not be subdivided into smaller compound periods. And that's, a little bit hard to interpret. But all that it's saying is something like this, that you say, suppose that you have an investment where you can receive 5% per year. That's just a name, right? It's a nominal interest rate. So that 5% can then be subdivided. So you can compound twice a year, or you can compound 4 times a year, or you can compound 12 times per year. So it's an interest rate expressed relative to a given time frame, so you can have a nominal rate that's a month long, or you could have a nominal rate that's 3 months long. So you need to fix a time frame that you're going to express this nominal rate. And then you can subdivide that into smaller and smaller compound periods. So generally in this experience, we're going to be talking about annual nominal rates, which is what we usually see in banks. So and so we've got this nominal rate that determines how much simple interest your money is going to generate. So let's take a look at an example where we start with $100. And let's suppose that we have a nominal rate of 50%, which of course doesn't exist anywhere. I wish it did, but there's no way.
Give you a loan shark.
Yeah, exactly. Yeah, so that's actually a perfect example. And let's suppose that we're going to compound twice per year. So, like I said, that nominal rate determines how quickly you gain simple interest. So we start at $100. and we've got the time span of 1 year. And so this is our first compound period, half a year. And so we invest this $100, and over the course of the first half of the year, we generate simple interest, so that at half a year, we've now generated half of what we would have if we had left it in for a full year, right? Full year, if we left it in, making 50% interest, we'd get $50, but it's only been for half a year. So we've made half of what we would have made if we left it in for a full year. So we now have $125. And then we compound, meaning this interest that we've made is not yet gaining us interest, but at that half-year mark, we compound it to where now the interest gets added to our account, and now that interest starts to make us interest. So this 125, you're getting the same interest rate, but you have a larger principal. So because you have a larger principal, now you're making interest at a faster rate. And so once again, we're making a nominal rate of 50%, but we're only making that for half a year. So if we had that nominal rate for half a year, we end up making $31.25 in interest. So I know these calculations are familiar. Anytime you teach pre-calculus, you go through a couple of these examples, right? But any questions before we go on?
But in high school textbooks, it's called compound interest.
Yeah, and that's exactly what's happening here, is that you've made interest, but that interest is not yet making you interest. So once you compound and you add it onto your account, now you've compounded, that interest is now making you interest. Yeah, so
So you end up doing more after a half year.
say that again. Yeah, exactly. All right, so
So is there an interest rate that we contrast the nominal with, that's like the actual or something?
yeah, exactly. That's called the yield. So the annual percentage yield basically says take the interest rate that you're getting in a nominal rate and compound it however many times you need to. The amount that you're getting at the end, that's called the annual percentage yield. Okay. Yeah. All right. So what we're going to do is we're going to sort of start to dissect this process. We're going to let A be the amount in our account. We're going to let R be the nominal rate. We're going to let P be the principal, or the starting amount. And we're going to look at a specific numerical example where we compound twice per year for 1 year. first compounding period, the amount in our account says take your starting amount plus the nominal rate times the principal starting amount times the time, right? And in this case, the time is half a year. And we notice that common factor of P, so we can extract that. So that's the amount in our account after the first compound. Principal plus interest. The second compounding period now, we've gained the interest that we've made. And so this is our new account value at the beginning of the period. So this is what's going to generate us interest. So the amount in our account says take the starting amount at the beginning of the second period plus
And R times that.
exactly, yep. And then times
1/2.
the time, exactly. So you've got that amount of money sat in that account for half a year. So you've got that time component half a year.
You take out the common factor.
Yeah, we got these common factors here. So we get P times 1 plus R, and we leave behind 1 plus, R over 2, and 1 plus R over 2. Questions? Anything so far? And so it's pretty easy to generalize this process. And just repeating it long enough.
So the general equation then is going to be P times 1 plus R over 2 to the power of n equals to the number of the compound periods or something like that.
Exactly. Yep. That's good, right. So the general formula is starting amount times 1 plus, let me just stick to my notation here, R over n to the n k, where P again is your starting amount, R is your nominal rate, n is the number of compounds per period, and K is the number of years. It depends on what your nominal rate is, right? So if your nominal rate is expressed in terms of years, then this will be years. So the number of
Compound period? No.
years. It's tricky. We'll just say years, because we're going to stick to where our nominal rate's expressed in terms of years, so it's not going to hurt us too bad. But yeah, if your nominal rate was, quarters, then K would be how many quarters you have, right? And then you could compound monthly, right? So if your nominal rate was quarters, and you compounded monthly, what would N be?
More.
3, right? Because your nominal rate's expressed in terms of
Quarters.
quarters, and so you've got 3 months per quarter. Yeah. So, but we'll just stick to the case where we're measuring our nominal rate in years. Okay. All right. So what we're going to do though is this equation. It works great in the case that you've got things expressed in terms of years, and you have multiple compound periods per year. But I'm going to make a little bit of a simplifying assumption throughout this whole experience. And we're going to assume, I guess I'll call it a class, huh?
It's offered right internship.
Yeah, exactly. It's a little bit lengthy. So in our class, we're going to assume that the number of compounds is always 1 per nominal period. And so what this does for us is it basically just gives us a little bit of a cleaner equation to work with. And so I'm going to call this the fundamental interest equation. And this is not something that I've seen elsewhere in reading books and articles and what have you. This is just a term that I use just because this equation comes up everywhere, and it just, I feel like it deserves this title. So when you have just one compound per nominal period, then the amount in your account is given by P times 1 plus R to the to the K. To the K. So questions on anything so far?
Yeah, just one question. When you put down in general, you put R over N. Now, I've seen that 2 was a constant, so how did you get, or how did you generalize that? Or instead of over 2, you
Yeah,
put
so
over N?
this was just an example, just to sort of get our, just to sort of see the algebra sort of flow through to this formula. And then after we've seen that for the case that n equals 2, now this is the general formula.
I understand. Yeah, thank you.
Good. So what I'm going to do, this equation works perfectly well. And you can certainly stick with this notation for the whole course. But I'm going to modify the labels very slightly because in finance, one of the most sort of basic operations that you need to do is translate the value of a payment into different times, right? And so basically what you're looking at here, you're looking at 2 different things. You're looking at an amount today, and you're looking at an amount in the future, right? So instead of labeling them A and P, those don't really tell us, those don't really guide our thinking of, present values and future values. I'm going to label these as future value equals present value times 1 plus R to the K. And just by making this relabeling, it really helps drive home the idea that there's a relationship between the present value of a payment and the future value of a payment.
Direct relationship.
Could you say it's future value sub K? Based on the
yeah.
K length of time?
Mm-hmm.
You
Absolutely.
have multiple future values.
Absolutely, yep. And that's a pretty common type of thing that you see. They'll label definitely different time periods of payments are going to be. So, not to bore you guys, but just for fun, we'll go ahead and work through an example. Where let's suppose that we currently have $1,000. So that's our present value. let's suppose that the interest rate we can get is 5%. And suppose that we invest that for 10 years. And we want to know how much we, right? And so, nothing to it. We've got our future value is equal to the present value, which was 1,000, times 1 plus the interest rate. And investing over 10 years. Again, we're assuming the nominal rate, sorry, the nominal period and the compound period are the same, so we don't have those extra n's floating around. And so you multiply this out, you get 1628.89. Yep.
What accuracy would you like for our decimals?
Pretty much second decimal place. Yeah, I'm not really thinking about rounding. Except for you guys. You guys have to keep as many decimal places as you can. But you have the computer do it for you, so. All right. So I had mentioned over here that really this equation represents a difference in time, right? We have a value that we've got today, a value that we're getting in the future, and this is the equation that relates the two. And there's actually a really just mind-boggling implication in this equation. And really, I don't know, I guess if you work with it long enough, it's not going to seem that mind-boggling, but when I was first learning this, my mind was blown. I was literally going around asking a whole bunch of people who knew, like, you know, business or management or what have you, saying, I'm doing this discounting thing. I just do not get it. I literally stared at this for like probably a couple of months before it finally clicked. But basically, what I'm getting at is that in the same way that a present value grows into a future value over time, you can also sort of turn that idea on its head. And you can say, suppose that I'm going to receive $1,000 in the future, then it's as if I'm receiving what present value today, right? So we are used to starting at the present and having it grow to the future. You can also start at a future value and say that's as if I have what amount today, right? And so the algebra, of course, is relatively simple. So we've got the future value given by PB times 1 plus R to the K. Then to solve for the present value, of course, we just divide by 1 plus R to the K. These reduce to give us the present value is the future value divided by this growth factor here. So basically what it tells us is that if we're going to receive a payment in the future, then it's as if we're receiving a smaller amount today that's going to grow into that amount in the future.
No question. I get it.
Good. So let's take a look at a couple of examples. let's suppose we can get 5% in the bank account.
I know.
I haven't seen that since I was a kid.
And suppose that we're going to get $2,000 in 3 years. Then it's as if we've received what amount today? So we receive this fictional money, put it in our fictional bank account, compounds at 5% over 3 years. We want to know what is that amount that we're receiving today. So, right, we've got all the key elements here. We've got present value equals the future value divided by 1 plus r to the k. So we're going to make $2,000 at a rate of 5%. Over the course of 3 years.
Oh,
592.59.
592.59. I'm getting something larger actually.
yeah, we should.
Yeah, 17.
Oh, it's 0.05.
Yeah.
My mistake.
Oh, I got you. Yeah, the 0.5 there.
I did that for 50%.
Yeah. So yeah, 1727.68.
Yeah, that's not right.
So it's really the same idea as what we've seen already, right? Money today grows into something larger tomorrow. Or in other words, something larger tomorrow had to start from something smaller today, right? $2,000 3 years from now started as 1727.68 and compounded over 3 years. So I'm not sure what took me so long to make that click. How do you guys feel on this idea? Everyone doing okay? I'm not sure what took me so long, but I didn't feel lonely at all because everyone I've talked to said the same thing. They're like, oh yeah, you know, inflation. I'm like, no, I don't think it has anything to do with inflation. I couldn't make it work in my head. But yeah, apparently a lot of other people hadn't really thought through this idea. But yeah, that's the basic idea is that you can pick up any payment and move it to any point in time and you get an equivalent amount, right? So if you take a payment today and move it back into the past, then when you move it back into the past, it's going to be worth less because it had to grow to the amount that you have today. Conversely, if you take that payment and move it into the future, it's going to grow in value because it's starting now and it's compounding over time, so it's going to grow in value. So as you move back in time, it's getting cheaper and cheaper, and as you move forward in time, it's getting more and more expensive, right? So anyway, that's the idea behind the time value of money. There's other components to the time value of money, right? So inflation is one of the components of the time value of money, that as the price level increases, your money buys less and less. So inflation is an element of the time value of money, but this is the more important aspect of the time value of money, is that if you have some interest rate that you can achieve, then your money is worth different values at different times just because it's compounded from something, or it will compound to something, right? So, all right, good. So, I do have one additional example, but it's a little bit, yeah, I think we'll skip that example. I think we'll.
Can you just present it to us?
Sure, yeah.
Yeah,
Is it okay if I just read it out loud?
Oh, sure.
So, a large future value and express it in terms of a smaller present value is called discounting. So what we've been doing so far is we've been using a 5% bank account. That we say, I could invest at 5%, I could make this money over time. And maybe that would be worth my while, right? But oftentimes you're not going to accept a 5% return, right? Sometimes you want a little bit higher, right? So there's something called the minimum acceptable rate of return. Minimum acceptable rate of return. And it's given the lovely acronym MAR, minimum acceptable rate of return.
Only word choice.
And it kind of is, actually. It kind of is, for reasons that we'll talk about a little bit later. We're going to call it the hurdle rate, just because that's a lot easier than saying minimum acceptable rate of return, or MAR. So hurdle rate is a much nicer way of phrasing it. So this is the rate that you're not going to invest until you get at least this amount. So if you're happy with 5% and there's a bank account offering 5%, that's great. You have met your minimum acceptable rate of return. But sometimes you want more. If you want 7% or 9%, then you have a higher hurdle rate. You're not going to invest your money until you get that higher rate, right? So let's take a look at what happens when you have these higher rates. So let's suppose that we have a future payment of $1,000. Let's suppose that our payment's going to happen in 3 years. And let's suppose that we have a hurdle rate of 7%.
So we get even less, huh?
Well, yeah, we're going to talk about that. We're going to talk about that in just a sec. Let's do the calculation. So we know the future value, sorry, the present value rather, is equal to future value, 1 plus r to the k. So the future value is 1,000. The hurdle rate is 0.07, and we're doing that over the course of 3 years. And that gives us a total of 8, 16, 30.